intelligent by using such kind of sort of tensor network. But the word tensor may be familiar to mathematicians because we talk about covariant tensor, invariant tensor, whatever tensor, for given representations from group. But here, of course, it's a generalized version, and that's why I also put the second word, that's generalized symmetry. So that's some conceptual, I think symmetry is very important since Newton's age here from UK, I think people understand this fundamental physics laws all from symmetry, right? Because it's better for the whole classical world and for our understanding for this geometry. But I think in the past 2 decades, I think great revolutions happens starting from kinetic physics. Some of you may heard about fractional quantum Hall effect, topological phases of matter, and also topological quantum computation, and all those fancy words in a simple conceptual, just we want to generalize this notion of symmetry. Yeah, once we generalize this notion of symmetry, it turns out the traditional field theory fails in the sense that even in many cases, we are not able to define such kind of generalized symmetry in the usual sense of continuous quantum field theory. So that's why this tensor network and the generalized symmetry, they are closely bounded to each other. Yeah, when we talk about generalized symmetry, we must evolve the notion of tensor network. But it's not surprising because I think nowadays we talk about a lot of AI, neural network, but this kind of quantum version of neural network, not surprising, can encode this generalized version of symmetry. So finally, I think this is kind of a very traditional word, CFT, everyone understood, because it's so important, like for standard model, for whatever kind of quantum field theory. Our starting point actually is conformal field theory. But still there are some subtle problems how to define this path integral measure, and mathematically I think it's still some controversial and some problems. So, and hopefully if we use this tensor network representation, now we call it as dual algebraic representation, can also give us some kind of completely new perspective for this older problem. So this work, mainly collaborate with my former students, and most work done during the pandemic because really nothing you can do, right? So you just work on this and doing many tedious calculations, and also my collaborator from Tsinghua University. Yeah, she's expert in CFT, so I really learned a lot from her. Okay, so I think let me firstly introduce what is generalized symmetry, because generalized symmetry, for ordinary symmetry, we know that's our classical work, right? We have this very nice Lorentz symmetry for our space-time, and also all kind of symmetry pattern identify these patterns for the classical work. But generalized symmetry is some kind of hidden symmetry in the quantum world. Yeah, if you heard about this quantum device like fractional quantum Hall effect, and also some very new discovered material called the fractional chain insulator, which means we can realize topological physics of quantum matter even without magnetic field. And those are very important resource for the future quantum computation. And because those kind of models also contain certain degeneracy pattern. In all the days, once we see some degeneracy, we know there's some symmetry, like this hydrogen atom, different degeneracy pattern. We identify the different symmetry according to their irreducible representation. But once we see some kind of new types of degeneracy, which depends on the topology of the manifold, then we can also summarize those degeneracy formally as some hidden hidden symmetry. But maybe I'm fine to talk to a mathematician about category theory. So all these hidden symmetry, you can think about it's a generalized version of this ordinary group symmetry. And also we know there's a very famous Takanaki duality. Once we have this group symmetry, we can always promote it to naturally category theory by using its irreducible representation. We know this rep G is a very natural fusion category from group theory. So from mathematical point of view, this kind of so-called topological phases of matter, they just a representation of picture, the conjecture is that if we want to discuss critical system, like from conformal field theory, or gap system, whatever phases of matter we want, they can all be unified from a high-dimensional point of view. That's the concept of holographic. Like our three-dimensional world, 3 plus 1D world could be very complicated, but the conjecture is that maybe there's some hidden 4 plus 1D world, which is purely topological. I think that's also many works done by Zheng. A lot of calculations, involve spectrum sequence, covariance, spin covariance, also very hard mathematical problem. But the conjecture is that once we know this topological phases of matter or category theory or high category theory in high dimensions, maybe we have a complete understanding of our fundamental works. So that's the bigger goal, but we still live far from there. It also includes this kind of, as a specific case, we can even rigorously reproduce this so-called ADS safety duality. That's all along this kind of line of thinking. From this cartoon, you will see that if we have some object in one-dimensional height, then we just make a projection. You can projection to a sphere. Suppose this is kind of smooth. You can think it has a gap space, like a conformal field theory, and this is kind of a square. You can kind of gap the face, but that really depends on what kind of projection you want to use. That's the simple physical picture. But now, for practical purpose, we also want to end up with something computable, mathematically rigorous, and also some kind of models and algorithms proposed by Prof. Finally. I just visited him yesterday, and also Danfrey from Harvard. I think for mathematicians, they can describe this kind of conjecture in a more precise terminology. So suppose we have some TFT for the bar. I assume everyone familiar with the notion of TFT, like Zheng-Cheng theory or its generalization. Then we can specify the so-called topological boundary. Topological boundary just means in terms of kind of metaphysics, just some kind of gap boundary. So let me go to the low-dimensional example. For 1 plus 1D system, you can think about this kind of boundary defined on the surface of the cylinder. So suppose we have this surface of the cylinder, and the whole cylinder is a 2 plus 1D system. Okay. We have x and tau as tau is imaginary time, and we have the real system. We are interested on the surface. Then you can imagine that in the middle of this cylinder, we can just dig a hole. Then on this small hole, we can do in this kind of looking kind of method a plus insertion, but in mathematical terminology, we just fix the topological boundary or symmetry boundary. Once we fix this boundary sector, then you can think about you can push this this kind of boundary all the way to the physical boundary. So that's the picture here. We can push this, or in terms of the sandwich construction, we call collapse sandwich. So this row is really the physical boundary. It's kind of a dynamical boundary. Depending on how we want to choose this projection, it could be either gap or gapless, whatever. That's a realistic world despite this row. So, but this symmetry boundary is kind of can describe the hidden topological symmetry. So why we want to separate this real physical world into this kind of sandwich structure? Because on this boundary we can identify this hidden symmetry in the realistic world. Otherwise there's no way to understand the hidden algebraic structure. So that's a physical way to understand the holographic picture and this same TFT formulation. So conceptually, we can view all the critical systems, including like a conformal field theory, as a very big zoo, right? So there are a lot of animals with very colorful schemes and very different shapes. So they're really complicated and beyond the knowledge of human beings, so far, especially for high dimensions. But the conjecture is that if we really make an X-ray of these animals, then we only see this bones or skeleton. So sometimes you just counting the number of skeleton, you know what kind of animal it is. So that's a conjecture that although we have a very complicated with a lot of deformations for this geometric classical work, but the essential data just determined by those skeleton or bones. It's just like a gene of the human being, gene of the animal. Just a finite number of data. Once you have that, you can almost understand the most generic property. And in future, we also hope with the help of like artificial intelligence, some of computing really complicated high dimension, in the sense that once we fix those skeletons, some topological data from category theory, we can generate this whole spectrum for conformal field theory, like conformal tower, conformal family. So that's the long-term goal. But of course, it's mathematically very challenging because BOA is what has operates all the story, and some mathematicians I know they just work on some types of BOA for their whole life. So it's really not an easy problem.
So you mean that only like Seagull theory or something on top of it? Seagull theory or something on top of it?
Seagull. You mean the TFT, topological field theory?
No, for CFT, yeah.
Seagull.
Yeah, so here our starting point is CFT, but actually it can be more general, including generic critical theory, even beyond the conformal field theory. And also you can make some deformation by turning on relevant operators from CFT, you can get QFT. So the whole conjecture actually is very generic. It's real world, this kind of so-called dynamic boundary can be arbitrary. But today I just show you some example as conformal field theory, especially just focus on 1+1D because we already have the Brasoro algebra. We have a lot of things we knew exactly. Then we can doing this computation mathematically rigorous, and also we can doing this algorithm. By using computer, we can also doing this calculation very precise, and then we can benchmark. So that's why today I will focus on CFT. But the whole program, I think, is very ambitious. We hope to understand our world in a completely different way.
By the way, so this slide is more like a cartoon illustration.
Yeah. So now I'm going to some mathematical rigorous thing. I can really talk about some mathematics, but I hope that we already have some agreement on the conception because my background is very different.
So the basic idea, just to summarize, I think just you are trying to encode some more complicated massless, gapless type of a theory or phases in terms of, for example, one higher dimensional topological gap phase, and which has smaller amount of data. So then this way of encoding maybe it's a skeleton that will capture something more general type of a gapless phase.
Yeah, it's kind of along the same line of thinking ADS-CFT. It's ADS gravity according to Palestina. I actually talked to him in Germany 2 weeks ago. I think here we even want to have a more generic pattern and include this ADS-CFT as a special example.
There's a title, by the way, SYM TFT, SYM.
SYM. Oh, yeah. Sorry.
Topological field theory, SYM.
Okay. So now let me go to some more mathematical analogy. So I believe people here are familiar with this work by Albemarle and also by Prof. I think that's very famous. Like a few decades ago, people try to understand this TFT, especially TKFT, and they invented this space-time model. And in terms of physical picture, nowadays we know the precise physical meaning of space-time model actually is a summation of all these topological defect lines. The word line of topological defects. So we also understand why they work pretty well, because this defect description, especially for TFT or TKFT, it's actually the dual description. So this kind of space-time model can be viewed as the duality of the usual transcendence formulation for TKFT. So in the past decade, we also generate this kind of paradigm to try to understand almost all the possible topological phases of matter up to realistic world, 3+1D, and it's pretty successful. If you are interested, you can also read some of our paper, and many of those also involve this complicated spectrum sequence calculation, which could be double exponential hard in Finally, in today's talk, so the goal is that whether we can generalize this program to critical system. So that's very ambitious. We try to understand this, for example, conformal field theory as specifically 1 plus 1D, also encoded in this state sum model. Sometimes it looks like a little bit strange because if we have conformal field theory, we have this lattice regulation. I think people knew this about a long time ago in the STEMAC models. We can realize whatever CFT you want by constructing certain STEMAC model. But typically, those STEMAC models, they have very complicated spectrum and only these low energy sectors consistent with the CFT description. There's always jumps at UV cutoff. And also, people think about lattice model for the UV complete CFT is impossible because we always introduce certain scale. But here, the idea is that if we can really make some state sum model, which is the analog of the Dykov-Witten and the Prof Bejour, if we can make it to be well defined on arbitrary triangulation, then after we sum over all possible triangulations, we can remove such kind of scales and recover the whole conformal numerals. Of course, in the exact construction for any given network, it's not a conformal invariant. Even there's no sense of conformal invariant. But the mystery or interesting thing is that if you compute any physical observable, like correlation function spectrum, you will see all of them exactly the same as the prediction from conformal field theory. So that's the magic. So it's kind of conformal field theory even without conformal symmetry at the construction. Okay. And also, in terms of numerical computation, we hope we just has almost a finite set of data. Just some small data set, you just have primary fields. The information about primary fields, we can already capture the whole set, and the descendants can be generated automatically. It's like a generation. So that's a precise meaning of optimum. So this is really our 15 years dream. So sometimes it's really like a nightmare because it's very hard to do this. So now let me just starting from this very classical and simple example. I think everyone work with for STEMAC model, just a 2D classical IC model. It's a famous model. First, the exact solution by Ansag and later by Yang, C.N. Yang. So now we use a different way to understand this model. Namely tensor network, but it's also naturally just a very kind of discrete version of path integral. So suppose we have this 2D STEMAC model on the square lattice, and then we can define this checkerboard this checkerboard U lattice, potentially the checkerboard lattice. So the way we're doing this, because we cover each bound once and only once, right? Then you can very naturally think about we can encode a STEMAC weight on each bound. Like if all the spin are up, just explain 4 bit, and the up down configuration just explain -4 bit. Other configuration just 1. There are many different ways you can do this, but that's the simplest way. So we can also do this for quantum circuits model.
So how do you exactly choose a dual lattice?
It's a checkerboard.
Doubling the.
That's a checkerboard lattice. So the way is that you have many different ways, but in this simplest way, there's no overlap, right? The checkerboard lattice is called sharing, and you cover the bound once and only once. Then you can easily count this statistic weight. But that's not important. So in some quantum model, you have more complicated tensor. But the conclusion is that whatever choice you can use, this tensor is always local because the model itself is local. So this tensor in some sense is just the kind of if you take a log of tensor, something like the local action. Because the model is local, so the tensor is local.
Just make sure. So this is classical spin.
Classical spin model.
So spin only up and down, and degree of freedom is on the right side of the white, the red sides, the red. Red sides. And a white circle that connect the both sides is try to specify the tensor T. And you just give some weight, but that factor is positive or negative due to just remind us due to just suppress certain interaction. because you want to favor, for example, maybe more.
No. Here you just write down the exact step back weights for each bar. Yeah, all the up, that's of course it's a classical IC model with ferromagnetic coupling.
Right.
The local Hamiltonian, just a summation over this minus the near the label, sigma I, sigma G. So if all up, exponential minus 4 beta just exponential minus beta h, right? So that's the Harding function. Yeah, so if you have all up, then this 2 minus sign cancels, so you get this exponential 4 beta. Yeah. You have up, down, then you get exponential minus 4 beta. So other configuration can examine just 1. That's it. Okay.
So the Hamiltonian has a minus sign in front of the
Yeah. It's zero. Yeah, but it's the same thing. Unsquared lattice ferro and ferro is the same thing. Yeah, but of course that's a simple example, but you can play a lot of models. So now let me also tell you some simple and traditional way how we can deal with such kind of tensor network. Yeah, people developed this kind of tensor network called discretized passing interval formula. I think 2 decades ago, just to try to make it possible for precise computational algorithm. Yeah, so in this simplest way, we can view this tensor as a matrix, right? Because we want to do some computation, but the exact computation, of course, is exponential hard. We want to use some approximation. So the simplest approximation is that we view this tensor if we combine this left and the down leg as the row and up and the right and the column. Yeah, then we can do in this best matrix approximation as a single value decombination. We decompose this big matrix into this unitary and positive diagonal and another unitary. Yeah, then for gap system, so suppose it's away from critical temperature, you can prove all these lambda, they just decay exponentially. And then you can just truncate the tail, you can get rid of the degree from you don't want. You can kind of make some approximation along this line in this figure. So so if you're not familiar with about this tensor network, I think this is a typical convention. If we make a summation, it just means we make a connection. It's something like in the convention, in the Einstein summation. Yeah, so now in this figure you can see after we're doing this singular value decombination, we can define this rank 3 tensor as u times this square root lambda, and another rank 3 tensor as v delta times square root lambda. Yeah, then if the spectrum decays exponentially, we have a controlled truncation. So we can deform this rank 4 tensor into this 2 rank 3 tensor. Then the whole lattice just from the square to the octagon lattice. Then the second step is exactly. We just sum over all the links on the small square. Yeah, just shrink this small square to a single point. Then we successfully realize this cross shrinking. Okay. So we do this again and again. We can get a very precise result if we do away from it. Oh, T prime? Yeah, T prime just like you sum this for that exactly. You get a new tensor. Yeah, so you can make a simple counting, like in this step you split 1 tensor into 2, but in this step you further shrink 4 tensor into 1. So overall you reduce the lattice number by half. And actually you rotate the lattice, right? So it seems a little bit complicated. But anyway, yeah, it's a very nice algorithm and it's controlled away from critical. Sorry? Consider what?
I think fewer amount of data, right? Less data.
Yeah. So the key is that this diagonal line, there are single values. If expand the k, you can effectively truncate, right? Yeah. So after you get an RG and many steps, in the end, if in the gap phase, just get something very simple. Like for isomath model, we have 2 different phases: symmetry breaking phase or disorder phase. Disorder phase, trivial phase, just end up just with 1 component. All the elements just 0. Here, symmetry breaking just direct sum. It's a dimension 2 tensor. You have 2 different sectors. It's 1. All the others just 0. That's very simple.
If you continue doing this kind of
You like doing this to some RG fixed point. Yeah. So that's the notion of fixed point. Okay. Because for gap phase, we know this correlation is just equal to 0 at fixed point.
Do you mind to remind me just one thing? So there are 2 steps. One is increase splitting one of the side into
yeah.
two sides.
In principle, you can increase this boundary dimension.
Right. So just remind me. So is there some kind of canonical, some way you are doing this? How is that step down? I mean, reduction probably is easier. You just do some summation.
Yeah. Here, just a singular value decomposition. So that's a canonical way. Right. In the next page, I will show you this very exact cost function.
But how about A? Just the step, maybe the figure A is you increase one side to two sides and.
Yeah. So on the AB sublattice, you do this in two different ways. So that's how you deform this into this octagon lattice. On A sublattice, you do in this way. On B sublattice.
But just make sure. But do you copy the data twice just to the site? Let's say the original site become two sides. Do you just copy the data to two other sides? Duplicate the data? Or
no. You're doing this singular value decomposition. It's very precise.
I see.
It's the best matrix approximation. But still, there's a trouble here. If you really sit at a critical point, then of course, if we think about we have infinite computational resource, like we can keep this singular value as big as possible. If we have a really powerful supercomputer, we can still simulate this pretty well numerically. People can even prove this algorithm has the same power as density matrix renormalization. So that's a very standard algorithm for this 2D classical or 1+1 quantum system. So that's why it still works well numerically. But if you ask a question mathematically, whether this tensor really approaching some so-called fixed point, it's not. You will see that if you increase this truncate dimension, then all the lambdas, they become more and more degenerate. Eventually, they almost become the all degenerate to one. So that means this tensor sits at a critical point. There's always drifting. You never reach the actual critical tensor mathematically by using this very simple algorithm.
But even for Isaac, you should see it, right? On your previous example, if you choose beta critical, then this wouldn't work like
Yeah. If you choose it at a critical point. So now we try to.
By the way, just make sure. Is this still a classical model?
Yeah, classical. In today, all my talk is just a classical model, nothing else. No quantum at all.
If you start with an artist model which is not a CFT, especially, can you do this?
This model, you just need to tune this temperature with so-called critical temperature. Then the low energy part will go to CFT. But of course, this is not exactly the same spectrum as CFT because you always have some jump at UV cutoff. If you choose triangular lattice, whatever geometry you choose, then this UV cutoff is very different from CFT.
And if we would have a fixed point meaning, you could do this.
So here you can see it's actually never really approach this fixed point at a critical temperature. So now we know there are some jumps in the algorithm. So that's why we also know why it's never approaching this real critical fixed point tensor. So the key is that how can we get rid of the jumps? So before doing that, I'm also briefly mentioning that there's some very interesting perspective from conformal fields here. Looks like already many important kind of idea in this algorithm, although it does not work in the end. So the first thing is that you take a careful look about this so-called SVD decomposition, how we decompose the rank 4 tensor into rank 3 tensor. Because for this rank 4 tensor, basically you can think about for bigger system, it's some kind of evaluation of this Tanning function with open boundary condition. Basically, you can view this as some kind of 4-point correlation function, right? Roughly speaking, if you're doing this kind of RG scheme for many steps, in the end, it's a cost-linear system and involves some effective degree freedom on the boundary. So basically, it's something like a 4-point correlation function. And at a fixed point, you should expect this kind of decomposition to be exact because we know for CFT we have crossing symmetry to guarantee this kind of decomposition. Of course, the second step is probabilistic because so far for critical system we can never reach the fixed point. But if we assume we have some improved algorithm, we can reach this critical point. Then this tensor becomes still invariant. It's kind of maybe natural candidate for CFT. So finally, it's a consistent condition. It's kind of about physical measurement. If we doing this so-called transform matrix calculation, basically if we trace this tensor from left to right angle, left and right legs, it's a meaning we put this network on the cylinder, we compute the transform matrix for the cylinder. So that's supposed to be the spectrum of the CFT. So we hope this can match all the CFT spectrum, and we can give rise to the correct scaling dimension. And for the last step, we can actually examine this even for finite system. Because this is algorithm is the same powerful as the MRG. So if we just simulate a finite system, which means we're doing RG for certain steps, let's say 10 steps, then we stop. In that case, if you increase a decut, like 100, 1,000, even 10,000, so on and so forth, if it's really big, then you can actually give rise this spectrum very, very close to CFT. So that's also why this kind of algorithm looks like optimistic. The only such problem is that we cannot have a well-defined fixed point tensor. But from all the other aspects, it really looks like a CFT. Even give rise to the correct spectrum, low-end spectrum as a CFT. Okay. So now we try to go back. How to fix this fixed point tensor problem?
Sorry, let me just maybe people follow that, but let me try to summarize. And also people should feel free to ask questions. So you start with maybe lattice model, which might look more like square lattice, and you take some large size system limit, and there are some relation that you try to identify the boundary of this square lattice as like full boundary condition somehow. So that's correlated to some 4-point function you're thinking about. But you contrast the boundary on one dimension, and then remain 2 dimensions.
Put the model on
so,
the cylinder.
So the scaling dimension is read as the 2-point correlator functions.
That's a 2-point correlation, basically give rise to the scaling dimension. Yeah, that's correct.
But then you are reading some of the eigenvalue to
just this. You take a log of the eigenvalue. Here you just diagonal this transformation.
But there are various eigenvalues probably from it.
Sorry?
There may be various eigenvalues.
They correspond to different scaling dimensions.
Scaling dimensions.
The descendants.
So
that's a diagonal basis. If you're familiar with such kind of problem. In STEMX, sometimes people also call the transform matrix of.
Right. So how do you know which one might be more like primary type of?
If we diagonalize it, you know all the scaling dimension, and later I will show you data. You can identify which is primary, which is descendants.
Okay.
You can have the whole conformal tower. You can even compute the conformal spin, and then you can even compute the OP coefficients. A lot of things you can do. But now we try to fix this fixed point tensor problem first, because it looks like it's very optimistic, but still we have some problem for the second step, right? So the way we fix it that trace back to these older days about the definition of renormalization group, because in Wilsonian renormalization, we want to integral out this quantum fluctuation in the momentum shell, and in real space that means we really integral out this quantum fluctuation in some small scale. That's why here we need to actually optimize over patch, because if we don't have this minimal patch, there's no notion of quantum fluctuation at short range scale. And also from the modern perspective of quantum information, we want to eliminate this so-called local entanglement. So here you can see that if we have some kind of quantum entanglement only propagated in this local circle, especially in our early work, we also define this so-called corner double line. We can show that it does not contribute any long entanglement for the whole system. So mathematically, you can define this as a very precise cost function. In the TRG, the SVD basically is vast matrix approximation. We call it single point approximation. So it's just a deal with a single point. So here we really optimize over these 4 points collectively. So that's why we call it a loop. It must involve some minimal loop. And on this loop, this algorithm also very standard, because it's just an 8-side DMRG with periodic bound condition, or 8-side MPS. If you're familiar with this algorithm, you can also just download some TensorKit code online, and you can optimize this pretty well. Once we replace the cost function by this one, then you can see some magic things happen.
Sorry, TRG stands for what kind of renormalization group? T is just
Tensor renormalization group. That's the original one by Michael Levine. Yeah, now we also call it Levin and Norway, I think the second author, TNR. Yeah, it's kind of different kind of tensor network renormalization group algorithm. But without this loop optimization, you don't eliminate this quantum fluctuation at the shortened scale. Then you never reach the fixed point for critical system. So here you can see by using this loop optimization, we can really reach critical points.
So can you explain again the loop? Yeah.
Oh yeah. The loop just means now we want to optimize this 4 tensor. Yeah. This 4 tensor contain like 8 legs. You can view this as a very big tensor on this small patch. So it's something you can think about. It's a cutting function for this patch with open with open leg. Open leg just assembling all possible boundary conditions. Yeah. So we want to optimize this one instead of single site. But if you're familiar with quantum field theory, you also have some feeling. This is something just like a so-called tree level approximation. But that's of course in momentum space.
So the
so this is something like a one loop. So in the actual RG scheme, the one loop correction is very important. Yeah, without the loop correction, you cannot treat this vacuum correlation in the correct way.
Just to understand, so it's like when you are contracting the tensor, like you care about how the loops go.
Yeah.
Okay.
Yeah, because here maybe something jumps in the middle. So in this algorithm, the powerful thing is that we can get rid of the jump in the middle. We only care about what happened for this outside boundary. Yeah. But here for single site, you should precisely encode all the information. So that's why it fails for critical system. We know there's a lot of jumps. Different UV scale spectrum is very different for different lattice systems. But in this way, this algorithm kind of we can do in this so-called entanglement filtering. So in the end, we can get rid of all these UV kind of details. Yeah. So then in the end, actually you can see whatever kind of starting point, you end up with some universal fixed point tensor.
Well, just make sure. So I mean, earlier you have another scheme that has a different contraction that you say it's only work for the gap phase. But
no, it's not a different contraction. So it's conceptually different.
Conceptually different.
Yeah. So here just like whatever lattice you do, if you just do a single site, or we call it tree level approximation, you never end up with a fixed point. So here the loop is crucial. Yeah. So the loop is one-dimensional height and a single point. Actually, this TRG, if you're familiar with mathematical terminology, you draw this dual lattice. It's just basically retriangulation or Paschen move. But typically Paschen move in the 2D graph do not involve loop. Yeah, so this loop in this kind of generalized Paschen move is very important. Only in this way you can get rid of the shortened non-universal part information in the fixed point tensor and make it possible to even define this fixed point tensor. So here it's pretty large. 2 to 40 is already way beyond the thermodynamic limit. Yeah, but here we stop typically at 40 step due to the machine error. And even with a very small boundary dimension, d equal 20, you can see it's already 5 orders of magnitude precise than the previous method. Yeah, the reason, of course, you optimize over 4 tensor, it's much easier to optimize just on one tensor. It's a collective optimization. So
and
that's why it works so amazing.
Excuse me, you say this realized Cardano's old idea in which sense?
Yeah. So I think in old days, Kalanov want to use this kind of block RG, but it fails because it introduces longer range interactions. That's why the current AI not so efficient because especially for neural network, it's kind of the same idea as real space RG. But here, the key thing is that if you're familiar with the DMRG algorithm, in this kind of loop, we call it swap. So in this swap process, you can generate new bases. Yeah, so that's also the crucial step in real space RG. At different scale, we require different bases. It's no longer this broad speed. It should be some collective basis. And in the end, you will know that actually it's a conformal basis describing this primary and this descendants. So that's why this algorithm is so powerful. To get rid of all the garbage at each different scale. Okay. Yeah, so now it looks like everything pretty well. We just try to read out this fixed point tensor, then the job is done, right? But unfortunately, the real life is much tough because this tensor numerically, if we end up with some fixed point tensor T star, there's always very subtle so-called gauge invariance. Yeah, so the tensor is not uniquely defined because for whatever tensor, if we apply this invertible transformation like lambda inverse on both sides, yeah, they connect together. They just still describe the same tensor network. So it's defined as an equivalent class over this gauge transformation. So it's really hard to fix all the gauge. So that's why, so this model is not easy to see the structure here. Although we already have the fixed point tensor almost 10 years ago. So until 5 years ago, we work on some different model. Yeah, so this model called the Q state clock model. It's a generalization of this IC model. But IC model is when Q equals 2 is the IC model. But this model have the nice property is that there's two critical points if Q is bigger than 5. The TC2 is rather universal. It's a famous BKT transition, won this Nobel Prize almost 10 years ago. You will see even for different Q, this critical point described by the compactified boson CFT have the same compactification radius, 2 square root 2. Then we were able to examine that whether this lattice regulation really matter for the fixed point tensor. Now you can see that we compare different Q with 8, 9, 10. Yeah, up to some numerical error, in the end, the tensor almost flow to the same values. Yeah, even starting from different UV lattice model, the fixed point tensor looks like highly universal. Of course, in order to get these data, there's also some small complication. Again, it's a basis choice. Yeah, when we have this minimal 2x2 block, then again we can do the same trick. We can glue this like up and down indices and make a transform matrix. Once we diagram this transform matrix, suppose we already set at the critical point, RG fixed point. Then we should expect the basis just labeled by primary and descendants. Yeah, because basically this transform matrix is like a 2-point correlation function. So now this new basis, after we put on the original tensor network, in this new basis, all these are labeled by like it's a lag R1, R2, R3. Yeah, it's a rank 3 tensor you can imagine, and they have different lags. So the lag is just labeled by identity and alpha, beta, gamma. Yeah, they just label this primary or descendants, right? So on and so forth. Yeah, so now you can look at this actual number of the tensor. So you can see at critical point, they're not decay very fast. Yeah, they actually decay in a kind of polynomial way, not the exponential way. But now we try to fit this fixed point tensor, try to understand the explicitly mathematical structure. Yeah, what this kind of tensor looks like.
Sorry, what's alpha, beta, gamma?
Oh yeah, it's just like when you diagonalize this transform matrix. The question related to all the questions, so you have many eigenvalues. So the leading eigenvalue I call the labeled by I. That's the vacuum or identity sector. Yeah, second largest labeled by alpha and beta. Yeah, it's just ordering all these kind of eigenvalues. Yeah, from the CFT perspective, if you diagonalize this 2-point correlation function, they correspond to this primary and descendants. Yeah, so on and so forth.
So from this table, what can we read from? Like how many primaries, how many of them are descendants? Or?
So kind of alpha, beta, gamma, delta. Yeah, that's all the kind of primary here in this table because you can show the descendants have a high kind of skin dimension. They do not involve in this table. Everything just the primary actually. Yeah. So alpha is the first primary, beta is the second primary, and it's a kind of just the U1 completed by both on CFT. Everything is abelian. So the primary just labeled by the in the next page I will explain more. Yeah, basically just labeled by the charge. The charge is plus, minus 1, and plus, minus 2, and 0. That's the 5 sectors I listed in the previous page. Yeah, here because the compactification radius is also bigger. That's a 2 square root 2. Yeah, so all these m, because they compacted by boson should labeled by both E and M. And M is not relevant because also generate very high component dimension. So we just fix M to be 0. Yeah, then basically the fusion rule very simple, just U1 child conformation. Yeah, so here just list all these the leading E sectors. Yeah, with charge 0, charge plus minus 1, charge plus minus 2. Then you can see that the previous page, all these data, some with certain numerical approximation, can be nicely fit as a three-point correlation function. So that's a major observation in our previous work. And also we can fit some fundamental distance, some kind of miracle distance involved for this fixed point tensor. It looks like very strange because CFT is supposed to have no any priori scale. So, but later, after we understand the whole structure, we will realize this kind of scale is not unique. It's something like a gauge choice related to the conformal transformation on how to construct this fixed point tensor.
How should I read the label of phi from the triangle tensor in the?
The label alphabet.
Okay, E1 and M1.
Oh yeah, so all the m set just to be 0. We just choose this lowest kind of scaling dimension. So m just 0. Then this alpha, beta, gamma just labeled by 0, plus minus 1, plus minus 2. Then I can just fit the tensor as this very nice as this kind of very standard three-point correlation function for CFT. So they are corresponding delta, the scaling dimension, you can just read out from this formula. So you put the delta there, then you put this fundamental scale here, then you can see this formula just perfectly generate the previous table. And after a certain normalization, you can see that the so-called OP coefficients, they all take the expected value, either to be 1 or 0. We just plot the non-zero components, so they are intrinsic close to 1. So that's numerical observation. So it's something like experiment. Okay, I think I already spent a lot of time. So maybe in the next maybe 15 to 20 minutes, let me just explain this mathematical structure from this kind of observation. Why this fixed point tensor will look like this. Now we have a very natural connection, or maybe the fixed point tensor, just the 3-point or 4-point correlation functions, right, from our previous kind of observation. But unfortunately, such kind of conjecture is incorrect. Although some Japanese group, I think, maybe 2 years before our work, they also claim maybe just a 3 or 4-point correlation function. But we knew it's actually incorrect even 5 years ago when we first finished our numerical work, because we can just a very simple examination, the so-called condition B and C is not satisfied. So looks like everything is not very nice, but still there's some trouble. The reason is that if you're familiar with the story of CFT, you know the 4-point correlation function for CFT can be naturally decomposed into 3-point summation of 3-point correlation function. But if you use this a 4 3-point correlation function, you want to put them together, you never reproduce the 4-point correlation function. And also, if you're starting from this 4-point correlation function, you just trace 2 legs and want to make transform matrix. You also never get a correct spectrum. So that's a problem. Okay. If we want to think about this more carefully, why this does not work, it's also kind of natural, because if you make a triangulation of this 2D manifold, you always end up with some corner. And a corner can be regarded as conical singularities. So maybe this can be regarded as a certain version of correlation function, but it's a correlation function with conical singularity. But I'm not a mathematician. I heard some friends doing this mathematics told me that maybe conical singularity sometimes do not affect primary fields. So that's why we can still fit it very nicely as a correlation function for primary fields. But this never works for descendants. So that means the whole structure is going to be much more complicated. Because the descendants descendants is not a simple correlation function. So that's why the whole thing cannot work. But we really try to work with these descendants with conical singularity. It's really hard. So finally, we just try to fix this by getting rid of the corner. We just cut the corner. We think about the triangulation with chop the corner. So if there's no corner, you can think about if we're doing some RG scheme, go to this fixed point tensor. They should be replaced by conformal bounding condition, right? So once we have this conformal bounding condition, then you can think about it further doing RG, then we can extend this conformal bounding condition. So in the end, it will be looks like some disk. Yeah, all the boundary of the disk with conformal boundary condition. But still, there are some subtle things because here, through different column, they correspond to different conformal boundary condition. So when they match, yeah, here you will naturally end up with the so-called boundary chaining operators. Okay. So now we have a connector, or maybe this can be regarded as the correlation function for boundary changing operators, or correlations for this boundary safety, instead of the usual safety in the closed string form. It's an open string form if you're familiar with string theory. Yeah, so here our experience also told us maybe this boundary safety or open string is more fundamental data. Yeah, if this is really can capture all the information for safety. Yeah, for some mathematicians, I think at the beginning they don't believe until they saw our data. Yeah, more and more of them accept this kind of conjecture. Okay, so now let me go to some details by explaining this structure from this rational safety. Because for rational safety, we know this boundary operator, especially for diagonal safety. Yeah, this boundary chaining operators just many to one map to this primaries, so it's much more simple.
Just make sure. So you say in the beginning sentence, the previous slide is the Japanese group about the fixed point tensor contains not just those. They fail to include additional data beyond 3-4 correlation function, but there should be some boundary data.
So in the closed string picture, this correlation function does not work. Yeah, so I think their work, they just examine our proposal for more models, for IC model, POS model. They end up with the same conclusion like this. Yeah, then they have a conjecture, or maybe the whole fixed point tensor just described by correlation function. But we knew that's incorrect many years ago. Yeah, it just does not work. So in principle, we should deal with correlation function with conical singularity, but that's also really hard, technically hard. So in the end of the day, we just chop the column. We try to deal with some smooth boundary condition without the column. Yeah, then we can view this as a correlation function of boundary safety. So that's the major idea. But still, there are some subtle details I will explain. Yeah, so the behavior of this correlation function is much better than in the closed string. It's an open string correlation function because you can view this conformal boundary as a deep rounds in the string theory. But of course, in many calculations, this closed string and the open string, they are equivalent, just a kind of basis transformation. Yeah, I think my time is almost there, so now let me just briefly go through this technical detail. But the conception is that the most important information is just this kind of structure. Yeah. Okay. So now you can examine this crossing symmetry, naturally satisfied. Yeah, even in the boundary safety. And also, the only subtle thing is that if we want to make the tensor fixed point tensor, want to make it scale invariant, we need to deal with this small hole, right? If we introduce a conformal boundary condition, there's also left with this small hole. So in the beginning, we just get rid of it. It turns out to be, again, incorrect. Because on the powers, you can easily examine. If we have a hole, we don't deal with just get rid of. We think about shrink to 0, we don't worry about it anymore. But actually, it's incorrect. Never produce the correct function on the powers. It's if we choose different conformal boundary condition, the torus function evaluation will be different sectors. Okay. So the whole difficult trick is how to deal with this holes if we really want to remove it. Now let me briefly review some algebra in the conformal field theory. I assume here everyone familiar. The simplest model just this Resora algebra. Yeah, it's some generalization of this harmonical oscillator algebra. And now we can also define this conformal boundary condition as the Ishbashi state with vanishing angular momentum tensor. You can view it as the kind of a coherent state annihilated by this annihilation operators. Okay, but the very nice and unique contribution by Cardi here. Yeah, I actually visited Oxford. Yeah, I think this work by Cardi is really nice. But Paul told me nowadays maybe Cardi has some health problem and did not appear in the department. But he did very important information, so a contribution for the so-called Cardi state. Because the usual Ishbashi state has a problem of this modular invariance. That means if we deform the boundary shape, it will typically change. So if we want to make the modular invariance, Yeah, we want to make it a Cartesian state. But the Cartesian state, you already see something really interesting. You involve this bulk is matrix. Yeah, so this we nowadays we know as the so-called bulk TKFT data. And it's the first time you can see this close relationship between this conformal field theory and the bulk TKFT. Yeah, how this bulk angle data must appear if we really want to define the Cartesian state. And if we also think about this this correlation function for boundary changing operator in BCFT is more fundamental to understand the CFT. Yeah, then you cannot avoid this bulk data. It's already there when you define this Cartesian state. Okay. For IC model, you can see that it's very simple. There's some linear superposition with very interesting coefficients for the expansion state. And now we try to shrink this whole in a rigorous sense that we want to project this Cartesian state on the identity sector. Yeah, that's the identity sector of the expansion state. Then we make a superposition of the Cartesian state. And finally, we can also design this imaginary time evolution to further make the expansion state to the real vacuum. So yeah, there's some calculation you can do perform this in an exact way. You can make the whole go to zero limit as imaginary time evolution go to infinite. Yeah, you really project to the vacuum sectors. Okay. Now the only thing you end up with just this additional weight. Yeah, because you want to project to the vacuum sector, the weight just involve SI0, which is a quantum dimension. Yeah. So once you have this quantum dimension, you put this correct weight for each conformal boundary condition sectors, then you can successfully eliminate this hole in a rigorous way. So now this people call it a cloaking boundary condition. Yeah, after we finish our work, we realize this Ingo Ronke, they already derived this 2 years ago, but unfortunately, due to the pandemic, we don't have time to communicate with them. But this is actually a very crucial step. Once we make this hole invisible in the sense that it's such kind of boundary condition, conformal boundary condition, is transparent to all the published beta line. Yeah. So in some sense, it successfully impose all the generalized symmetry for the fixed quantum tensor. Okay. Yeah. So that's the major result. Finally, let me just tell you the precise construction for this fixed quantum tensor. Yeah. So first, you can imagine we can, for any given 2D manifold, we may just make arbitrary triangulation. Once we have this triangulation on each corner, yeah, that's the thing we want to chop. We want to chop the corner. We assign conformal boundary conditions. Yeah, for rational safety, yeah, that's just a finite number of choice. Then on the link, we just assign this primary and corresponding descendants. So the tensor involves like 9 indices, but it actually decomposes into 2 pieces of data. So this Cij ABC is kind of the structural constant in front of the OP coefficients. So that's just a finite number of data, because especially for rational safety, ABC is finite, Ijk is finite. So the whole thing is finite. Then this alpha is something more complicated. Yeah, really involve geometry because a kind of infinite dimensional tensor. This capital Ijk involves all the descendants. Sometimes we call it conformal block. So this thing is something more complicated. But fortunately, in 1+1D, we can still compute this from Virasoro algebra in a precise way. But in high dimension, we don't know, but we believe something still exists, although there's no exact calculation. So finally, the important thing, we put this weight on for each vertices. It's something like a space-time model. The weight is very important, which is corresponding to the quantum dimension of the area. Okay. And this C, the structure constant, actually proportional to the bulk F single. Yeah, so the whole equation can be regarded as a Pentagon equation from the fusion category. And alpha is a conformal block of the 3-point correlation function. So on the upper half plane, if we're familiar with the computation of safety, you will know it actually decomposes into this structure constant times this conformal block. Yeah, we have a standard formula. But the actual simulation or calculation we want to do is for some disk, right, with the insertion of boundary chaining operator. Then we need to design some very clever conformal map. We also spent years to find it. Once we have this conformal map, yeah, we can just map this standard correlation function to the arbitrary geometry we want. Yeah, so that's the essential calculation.
So can I ask a question? So the way that I now read it is that F comes from the fusion category, right?
Yeah.
and then C's are the Clebsch coordinates.
C actually, yeah, it's something like recoupling constant is proportional to the bulk 6G symbol. Yeah, I will show you later.
Both of them, okay.
Yeah. So this is a C in some sense proportional to F.
Oh, so F is the solution of pentagonal equation.
Yeah,
and
it's a
C
pentagon,
is the solution of the like hexagonal equation.
Yeah. So the real hard thing is alpha. Yeah. So for any given bulk F symbol, you can see the alpha also satisfies such kind of condition. If you're familiar with category theory, that's the modular category. Yeah. So if alpha just get a finite possibilities of labels, it's the usual modular category classified all the gap boundary for the bulk TKFT. But here the subtle thing is that the label of alpha becomes infinity. So the reason why it's infinity because this alpha, not like in TKFT case, which is independent of the geometric information. So here you will see this alpha actually rely on this geometric information. Yeah, that's actually even in our original numerical fit, you can see if we choose this perfect triangle and some triangle with different shape, there's some very interesting square root 2 factor I did not mention. Yeah, so you can see that if we choose the triangle like in this shape with 45 degree, 90 degree, the correlation function fit, you will see this there's a square root 2. Which means the fundamental distance between this Z1 and this Z2 is the square root 2 times of that. So if we choose different triangle, alpha actually rely on this angular variable. So this equation can be regarded as an infinite number of equations. Sometimes we call it infinite variety of the modular category. Yeah, I also talked to Paul yesterday. Maybe it's also related to this so-called spectrum parameter in the Yang-Baxter equation. Yeah, so sometimes this spectrum parameter also gives you some geometric information in the Yang-Baxter equation. But although still there's some distance between CFT and the integrable model, but they all share this kind of same concept. Yeah, this alpha is rather complicated because the descendants actually define the geometry in the CFT. Okay. Now we just try to examine this by explicit computation. Okay. So yeah, still maybe just 5 or 10 more minutes talking about that. Slow. But here this technical part is very standard. Yeah, we just insert this boundary chaining operator at origin, then according to this state operator correspondence, yeah, we can design some very clever conformal map this applying to this small segment. Then we can just attach this small segment onto this triangulation with the chopped angle, corner. Okay. So now the only tricky thing is that this F, not arbitrary. We chosen this F conformal map such that when two of them overlap, they just satisfy this canonical delta function, something like orthonormal condition in quantum mechanics. Such that in the end we can just remove this segment for overlapped region. So we can find this very clever F, which is a composition of the three functions with gauge out parameter theta. Now in our calculation below, we just fix theta as pi over 4, but we can also do some different gauge, pi over 2. And it's very interesting that different theta choice will correspond to the different fundamental lengths we observe in the numerical fit. So now we understand that this kind of fundamental length in the fixed point tensor actually is a gauge choice. Maybe depend on our RG scheme, how we design this RG scheme. But it has nothing to do with the fundamental length in the CFT. So that's we don't completely understand. But from this construction, it looks like just some gauge choice on this conformal map. So the next step, we just map this with the insertion of boundary chaining operator to the usual upper rank. So this map is very standard. We call it G function. So the G function is very standard. But for F function, actually on different segments, still some subtle detail. We assume here is origin. Then in order to get this segment, we shift along x direction by 1. And for this, we rotate 90 degrees, shift by -1. And for this, we just rotate by 45 degrees. And then we have 3 different conformal maps on these 3 different segments because the shape that we attach on the triangle in 3 different ways. Okay. Then the composition just cut, F and G. So now we can do the computation like for example, primary fields. We just take a derivative of this conformal map, the origin. X1, x2 is the final coordinates when we map back to this cut back. So typically they are not set at already. So that's why how you can see this fundamental distance arises in the calculation. Okay. But it depends on how we define this f function, the theta. Yeah, so it's gauge dependent. So now, just to show you some numerical data. Yeah, even with extremely small boundary dimension, let's say it's 13, just evolve a few kind of descendants level. Yeah, we can show this like kind of crossing symmetry and this kind of scale invariant conditioning satisfied up to very high accuracy, yeah, 21%. Yeah, but this can be improved systematically. So that's a very good sign for the this actually eventually works. And also we can compare the conformal spectrum. Yeah, like we, in order to resolve more skin dimension, we make it a little bit bigger. Yeah, just constructed by 4 tensors for the transform matrix. Yeah, you put 4 tensors on the thing. Yeah, we can evolve. We can resolve a lot of skin dimension up to 3 or 4. So they are very close to the exact result. But here we always make some error because in the actual computation, in the computer, it's not possible, or in any analytical calculation, it's not possible to evolve to include all the descendants. So we always make some cut somewhere. But we can actually prove those cuts just corresponding to irrelevant relations. So yeah, they will not affect the flow of the CFT. But if you look at the numerical data, there's always some actually they are already very accurate. Okay, so finally we go back to this our numerical observation. Yeah, in the numerical observation is that that if we diagonalize this transform matrix and go back to this diagonal CFT basis, we can also fit it as a mutual correlation function in the closed field. Now we can see this fundamental scale in our construction. If we choose theta equal 45 degree, it's slightly different from the numerical observation. Yeah, we can see this very nice square root 2 factors, but the fundamental length is not bigger, it becomes 3.3, which means the tensor decay even faster, actually even nice than our numerical results. So in order to reproduce this numerical result, we choose a different gauge with theta equal to 90 degree. In this case, we just map this upper plane to the usual like strap, and the whole thing looks like a paint diagram. So in this case, we can see this fundamental length is exactly the same as the numerical observation, 2.4. We have some choice, but yeah, there's looks like this fundamental length bounded by separate. Okay. So finally, I also show you some other models, like the tri-critical IC model, and also Yang CFT, yeah, they all work pretty well. Yeah. So that means it's not just a coincidence for IC model. Yeah, we can even do this to this so-called holographic picture. Yeah. So there's a relation. So yeah, there's a question: what's the precise meaning of this structural constant C? It's not the simple CG coefficient. It's actually the coupling constant. If we rescale this alpha by some n, just some kind of number, and then this C can also be rescaled to C hat. This C hat is just a very standard 6GHG symbol in the bulk. So naturally satisfy the Handelman equation. If you're familiar with the mathematical representation for the so-called spinel wave function, yeah, that's describe all the possible non-parallel topological phase in 2 plus 1D, and you can see that this fixed point tensor actually can be naturally reproduced from this 2 plus 1D wave function. Yeah. This is the spinel wave function, the 2 plus 1D bulk. And you can see the very important components, topological components, the 6GHG symbol which is proportional to C, and also this omega weight. Yeah, so that's in the state-time model, if you're familiar, that's the weight on the link. Yeah. Already appear in this bulk wave function. Then you can just make an overlap with this conformal block. Yeah, this gamma basically up to some factor, that's a conformal block. So of course, the gamma in general is really hard because it's an infinite dimensional tensor, such that we want to include all the geometric information, and it's also relying on this geometric information of the triangulation. So this is non-universal, but this part is universal. So sometimes we just call this as a generalized symmetry for the CFT. It's universal data, but this is non-universal. It's a geometric data. But if we make this wave function overlap, yeah, that's the physical way to do this projection, right? We call it projection if we talk about quantum mechanics. Just means we make a wave function overlap. Yeah, that's the precise meaning of projection. And if you choose some different wave function, like you choose gamma equal to 1 or some other wave function, yeah, then you can realize this gap boundary. But here, if you choose this gamma proportional conformal block, yeah, you can realize this gap is boundary. Okay. So this go back to our very first page. We choose different projection, we can realize different phases of quantum matter.
Is it the series that you call that generalized symmetry, or why do you mention generalized symmetry here? Just make sure.
Oh, here just means in the tensor network construction, this generalized symmetry appears in a very precise way. Yeah, encoded in the C in the structure constant. So that's this appear in the usual classical CFT. In CFT, you want to understand this, you consider all the possible definite operators. It's really hard and tedious sometimes. But here it's very natural. It just appears in the first place. So yeah, I think a little bit longer, but let me just briefly tell you some unpublished new results. Yeah, this not only works for this rational CFT, but yeah, even for irrational CFT, like competitive boson, it's actually like 1. And here something slightly more complicated, but like we needed to use this conformal boundary conditions integral instead of summation, like Dirichlet and Newton condition, because I know some people in string theory, and this kind of competitive boson CFT is really important for string theory. But we realized that this kind of conformal boundary condition, you can also do some certain discretization by replacing this integral as summation. But we can show that area actually controlled in certain way that when replace it by discrete summation, we just get rid of some irrelevant operators. As long as this discretization value n is bigger than the radius of the competitive boson. So here, all these data, just like we take n equals 3, we already produce very precise conformal dimensions. Yeah. And also, there's a more exotic model. I don't have time to explore in detail. It's some very exotic. I believe some mathematician may be interested. It's a kind of very old problem. Yeah, the so-called STEMAC model, Q5 Potts model, the dilute Potts model. But the interesting thing is now if we set up the K and D parameter to be complex, the tensor actually will flow to some new types of CFT we call a complex CFT, with complex symmetry and complex scaling dimension. Because if you constrain it to be real, there's no kind of second order friction. You just you have some first order friction, weak first order. But you allow to go away from this real plane, then you get hit some complex CFT response. And all these kind of spectrum just from the analytical continuation, yeah, there's technical people believe maybe works for complex CFT. But we also examine our algorithm that we can actually reach some fixed-point tensor in certain approximate way. But because it's not a unitary model, it's not as stable as our previous unitary CFT. But I still have a hint that this discretized kind of formula is even useful for more crazy non-unitary models. So finally, so finally, before this talk, I also show you some new scheme we call a holographic bootstrap. Yeah, so this is supposed to be some new algorithm may generate new CFT in future. And even we don't know the Brasol algebra or the precise algebraic structure, we can just starting from this box fusion category, and by inputting this F symbol, which just the structure constant C in the correlation functions. Yeah, then up to certain integers, we can also use the technique called Zheng-Cheng Gu to figure out this scaling dimension for primary fields. Yeah, so once we input those data, we can make a approximate fixed-point tensor. Approximate in the sense that we just truncate all the descendants. Yeah, so this approximate fixed-point tensor just take this 0, 0, 0 components. You can see the function here actually is universal. The alpha here we can show it's a universal function for fixed triangulation. It's a function of this scaling dimension, but the scaling dimension can depend up to integers. So we can just input this tensor as the 0, 0 component, which means we cut all the descendants. Yeah. So if we cut the descendants, this bulk fusion equation still satisfied, the pentagon is satisfied. But this modular category condition just satisfied up to a certain error. But it shows actually even with some error, this kind of expansion always converge alpha 0, 0 plus alpha 1, 1 plus alpha 2, 2 is something like a Taylor expansion for this conformal block. Yeah. So our conjecture is that such kind of expansion is much better than the Feynman diagram. In the Feynman diagram, it not necessary to be converged. Yeah. If you expand doing this Feynman diagram expansion to first order, second order, third order, maybe 100 order just fails. But here we can we just conjecture there's always a certain convergence radius. Yeah. So if you have infinite commutation hour, you can do this very precisely. So the observation is that all these tensors, they just decay rather fast. Yeah. So even for critical system, if you look at this actual numerical data, you will see it's very amazing. Especially for rational CFT, you can see the third component is already just like less than 10% of the first one. So if you make a very wide truncation, you can already get this more than the 90% information for the CFT. So yeah, so I think the major message here is that previous mathematicians want to just try to understand the conformal field theory set at the exact CFT fixed point. We want to exact conformal symmetry. But here in this network representation, sometimes we call dual algebraic representation. We just emphasize this bulk generalized symmetry. So the conjecture is that for any given generalized symmetry, there is only finite number of solutions of VOA which is compatible with the generalized symmetry. And this algorithm can be regarded as a kind of algorithm to generate exact VOA. Yeah, so VOA, we just keep conformal block alpha 0, 0, 0, and you can design some suitable algorithm. Maybe in the end you can get the complete VOA in a very precise manner. Yeah, but we are physics, we never do anything exact. Yeah, just with certain enough accuracy, we are already very happy. Okay, yeah. So finally, here just conclusion. I think I spent a lot of time, but I just try to emphasize that this method not only works for CFT. Actually, we can add relevant or irrelevant perturbations into the CFT by tuning this weights in the hole. Yeah, you will see that this weights in the hole really important. It's kind of corresponding to this any quantum dimension from the bulk. If we change the weights, yeah, we can make CFT just flow away to some new fixed point, like this E8 state we already tried. Yeah, if we starting from vertical IC model, we turn on this sigma as a relevant perturbation, we can perfectly reproduce this E8 spectrum in this way. So this is a more generic way to maybe can replace this Feynman diagram, at least in 1+1 system. It works pretty well, and even allow us to study a lot of new fixed points beyond this integrable limit. And finally, there's also some application may be really useful for this high energy study like ADS CFT. And also I know there are maybe some string theory here. And when I was working at the perimeter, Luren there told me they're looking for some version of so-called discrete string theory. Hopefully on the worksheet we can have a discretized notation for the string, such that we can perform this non-perturbative calculation in a very precise manner. And it may be even useful for string field theory. Okay, thank you.
Thank you very much. We have many questions already, but any other comments? Questions?
Well, I think higher dimensional CFTs is workable.
Yeah, in our framework it's rather interesting because you can see the fundamental data here. You can kind of guess, but we don't have a precise solution so far. You can think about the general symmetry now. Tell us it's something like a tangent symbol on the tetrahedron. Yeah, so to replace this 6-digit symbol on the triangle. But once we have this tangent symbol, we also need to do something as a conformal block. But this conformal block, from our perspective, is no longer described as a correlation function for particles. It describes a correlation function for strings. So I think that should open a new direction. Tell us the correlation function for particle and the older fashion of conformal bootstrap would be not a correct way to understand conformal field theory in high dimensions. Instead, we should consider this correlation function for string, correlation function for membrane, such that we can understand this CFT in a completely different way. But we don't expect any exact solvable limit because here we even don't care. Yeah? As long as we have controlled series expansion, just like Taylor expansion, we don't care this function is exact or not. Yeah. Okay. de-Ising model, we already have some primary results. With relatively small boundary dimension, we can describe this critical Ising transition in very high accuracy using this physical kind of method. The physics is also very simple because basically it's just a symmetry in transition. Even with boundary dimension d equal 2, we can already evolve lots of like this quantum fluctuations surrounding infield theory, so it's almost already equivalent to this one expansion. So that's why this Wilson-Fisher fixed point we believe can be understood in this very precise but not exact way.
This will be around today, and we will probably just gather here to have lunch. If you have lunch, if you want to buy lunch or whatever, we can sit here and chat with this, and then if you want to schedule time to chat with this, and also give.
Yeah, we can discuss more after lunch.
Actually, people gather here for the lunch, so
Okay.
we'll meet here, and then we can chat more also after lunch.